How about now? Yeah, not much better, but okay, let's live with it. So, okay, so the first layer, which is at the very bottom of the file system stack, is a buffer cache, right? So essentially, remember how it works. It has be read, be write, and be release. And the typical use of the block is to essentially first acquire a block from the cache with the be read method, right? Remember, we looked at how caches work, how the buffer cache works. So essentially, we search through the entire list, find a block which has a matching block ID number and device number, and essentially returns it to you, right? And then on top of that, we said, okay, there will be a layer of journaling. So essentially, this thing which allows us start a transaction and then perform a bunch of writes, but instead of be write, we'll be using a different primitive. We'll be using a log write. And a log write is a different function, which essentially at a high level, it does the following. Let me make a drawing for you, right? Because it will be much easier to understand if we have a plan for what's coming here. So remember, the file system consists of multiple parts, right? And we skip some parts which you don't care about, but this one is a data area, right? So this is where the actual data is stored. However, there was a small journaling area here, right? Journal, right? And normally, be write would write a block straight into the data area, right? Remember, the inode area would keep a mapping. So the layer of inodes essentially sits on top of the buffer cache or parallel. So these are the inodes. Inode. And the inode says, okay, this is block number 55. This is where I will find the data for this specific inode, right? But if B writes directly into the data area, right? Then the log write first writes the block here in the journaling area, right? It writes it here, and it writes all the blocks within the transaction here. So there might be multiple writes. So you might do the multiple log write primitives. And so you accumulate a couple of blocks here in the journaling area. And at some point, you make a mark here saying that the transaction, for example, contains 2 blocks. At this point, you use the be write primitive to update the journaling area on disk, right? So you write it. At this point, the transaction is committed to disk, meaning that even if you lose power after reboot, you will find this number 2, and you will find the blocks in the journaling area because you were doing be write here, right? And even in this case, you then install those writes here into the data area, right? So normally, if you don't lose power, you first write this block number 2, like which contains this 2, and then you start installing those writes one by one, right? So essentially into the data area. And then when the transaction is done, essentially you install all the data blocks. At this point, you again cross this out and write 0 again here. That's saying that the transaction is now finished and the journaling area is empty again. So is this high level intuition make sense to you? Any questions about transactions and journaling? Let's take a look at how x86 implements them. What happens if you lose power before you write into the log? It's gone. So it's like it's never happened, right? But I mean, you will lose data. So for example, if your application says, okay, I computed 55 and I'm writing to disk 55 saying that my computation is done, at this point, you will lose this information, right? This write will never happen. But at least the file system will be in a consistent state. After reboot, you'll be able to open it and there will be no leaks. And actually, remember, I promised you to think about whether someone asked this question last time, that whether we can recover, whether this journaling is needed strictly for performance of recovery or for consistency as well, right? But, and I didn't think about it. Let me think a little bit more, I promise. And no one asked me on Piazzas. That's why I completely forgot until we get back here, right? But again, you got the point. So those writes are lost, right? So there will never be. But essentially, at a high level, what you're trying to achieve is that you're kind of moving from a snapshot to a snapshot. So essentially, imagine your file system in this snapshot is in some consistent states. Essentially, all the metadata about inodes and missing blocks, free blocks and available and allocated blocks is correct, right? You would say, look, if I would do those writes one after another and lose power here, maybe it's inconsistent because maybe you didn't like add another write, which is required to achieve the consistent state. That's why you say, look, instead of doing those 3 writes in the data area, I will do them in the journaling area, right? And then at this point, you say, look, I'm moving from one snapshot to another. At this point, you know that those writes, even after reboot, will be installed, and again, you will be in a consistent state, right? So that's essentially the idea behind journaling, right? And you're right. I mean, if you're intuitively thinking, okay, is it possible to implement the file system which stays in a consistent state without journaling? Yes, and people were doing it. So you have to very carefully order all the dependent writes and essentially make sure that the ordering is correct. And at least one file system on the FreeBSD operating system uses this approach. So I think it's called soft updates. But again, the logic of those soft updates was so complicated that only a few people were able to maintain the file system. At this point, you know, you're updating multiple parts of the file system, and there's always a chance that you're missing the logic of the order of writes. And essentially, that's why most modern file systems gave up on this idea and essentially revert to journaling. The disadvantage of journaling, an obvious disadvantage, is you actually writing the block twice. So you first write it in a logging area, and then second time you write it into the data area. So at least your write throughput drops by half, right? That's just because you're doing writes twice, right? But sometimes you also have to do reads, right? So to reread those blocks when you install the journal, so right, so it introduces its old performance penalty, right? Okay, so let's keep going here. So let's take a look at how this journaling idea is actually implemented. So as I was saying this, remember the typical use is begin op, do a couple of log writes, and then do an end op. And an end op, like we were talking about it last time, will check whether there's still space in the journaling area, right? Oh, hold on. It will check for whether there is still some concurrently running transactions, right? And like the file system maintains a counter of outstanding transactions, right? And you first decrement this counter, and only if you say, look, outstanding is equal to 0, right? Then you enter this commit stage, right? Else you just start sleeping, right? Waiting for the essentially for the you don't essentially you wake up everyone who might be waiting for other transactions to run, right? And essentially you skip this part where you do commit. But this is the most interesting part, the commit part, right? Essentially the first one just maintains the guarantee that there will be always enough space in the journaling area across multiple transactions, right? But the second part is actually does this commit. So, right, and this is where we stopped last time. So we were looking at this commit function, and we're trying to understand how it's implemented. And this is where we stopped the lecture. Okay, so the logic at a high level, the logic of the commit is clear to you, right? Because you say, look, I kind of understand. I understand that you should first write the modified blocks from the cache to the log, right? The question is, what is this cache? And did I explain the caching? I didn't. This is where, actually, this is where we stopped last time. So I skipped one important function, right? So I skipped the internals of this log write function, right? Because I got confused and I moved to the other slide. But really what happens here is, right, remember, without a transaction, you would do something like a block write function here, be write, right? with the transaction, you do a log write function. So this function is responsible for recording the write into the log, right? So let's take a look at how it works. So the log write function, we talked about it actually, yeah, maybe too quick. So the log write function maintains a list of blocks which are participating in a specific transaction in memory, right? And essentially, when you write a block with a specific number, this data structure in memory contains this array, right? So we actually talked about it. I'm sorry, I forgot about it, right? And there is a notion of log absorption. So essentially, if you write the same block twice, you don't have to record it in the transaction, right? You just say, okay, forget about it. I remember it. And at this point, no actual write is happening. Do you remember what is happening instead? So this data structure is in memory, and this is this log data structure. There is also buffer cache. This is buffer cache. So what happens? What happens to the block? I'm saying there is no write to disk. So what is instead happening? Do you remember? Say this again. Anyone? So what happens here that we record the block number, right? Maybe this is block number 55, right? In this log header, right? And then this, we just mark it as dirty, meaning that the operating system knows that this block in the buffer cache is dirty, which means that it cannot be evicted, right? It has to stay around for a while, right? So, and that's sufficient because we know that by the time we will get to committing transaction, we essentially will go through this log one element by one, right? They all will contain pointers to blocks, right? In the buffer cache. And essentially at this point, we essentially will write them with the B write into the journaling area of the disk. Does it make sense? So this is a journaling area. It's horrible. Right? Does it make sense to you? Essentially, so this log write function doesn't perform an actual write to disk, but instead marks the block as dirty and remembers the block number in the log header data structure, right? Later on, when we get to the point when we want to commit, right, with this function, we first will write the log, right, from the buffer cache into the journaling area. Then we will write the head. Remember, I was writing this number 2 in my previous drawing, right? At this point, the transaction is persisted on disk. So even if we lose power, we will reboot and recover it, right? And then we'll install transaction, essentially moving the data from the logging area into the data area. Then we will update the log header with n equals to 0. And then we will write the head again. At this point, writing this transaction, the size of transaction to 0, essentially crossing out this 2, right? This is the high-level overview of this commit function, right? So let's take a look at how it really works. So writing the log header is the following. So we are iterating through all the elements of this log header array, right, from the beginning to the end. For each of these blocks, we essentially we first acquire the block from the buffer cache, because remember, we only have the block number, right? So, and here this 2 element is the very first block, not the very first block, but the first available block in the journaling area, right? This is a journal. So essentially we get the block from the journaling area with the B-read primitive. We get the block which contains the data we want to write to the journaling area, again with the B-read primitive, because this is the only way to acquire a block from the buffer cache, right? And then we essentially say, we just copy the data from the from block to the to block, and we copy 512 bytes, the block size, right? And then we do 2 writes. At this point, we use the block write because this block write will actually go to disk. Remember, internally, it triggers this ID read write function, which essentially writes data to disk, right? And essentially, you write only 1 block because you only write this one. The other one is not even dirty, right? Because, no, actually, it is dirty, right? And a good question is, at what point you actually release it from the buffer cache? So I guess you can release, I didn't realize that it's possible. You can release a block, a dirty block with a be release function, right? Let's just double check that this is how it works. Let's just quickly take a look at the source code of x86. Let's go here. This is my, nope. Yeah, BIO. Just wanted to quickly double check that B release can drop the counter. So no one is waiting for it. This is what bugs me a little bit. So my impression was that this block is actually dirty. The one which we actually wrote on disk, but for whatever reason, the file system believes. Okay, I should admit I don't understand this. Let me double check. Do you understand my confusion at least, or you don't at this point? There were 2 blocks in the buffer cache, right? So one is the one which we were updating, right? This is the block which corresponds to the journaling area. And this is the block which we're writing to disk, so, right? So this is the, for example, a data block number 55, which we read into the buffer cache when we started doing this transaction, right? And then we did this log write operation, right? And log write operation marked the block as dirty, right? This one, to prevent eviction. And I don't get it, like I don't understand at what point this block will get evicted from the cache, from the buffer cache. Because in my opinion, you have to somehow unmark it. So essentially in this commit function, you should, okay, maybe I don't have the whole, no, not in the commit, but in the write log function, you have to mark it as a non-dirty, because at this point you have to throw this block away. You don't care about it anymore, right? So essentially you rolled it into this block, right? Okay, so that deserves some additional investigation. We'll do that later again. Sorry, already like two pending later things which have to happen, right? Okay, but at this point, yes. So we read the block from the log, right? Log starts from the log start, but then since we keep moving, right? So we keep incrementing this tail pointer. We're gradually moving forward. Then we read the actual block. It's in buffer cache, right? And we know the block number. We copied the data, as I was saying. Then we wrote the blocks and released both blocks, right? At this point, the block is still in a buffer cache. The counter is 0, but it's still dirty. That's what bugs me. Okay, but we'll come back to it. At this point, we have to write the head. The write head essentially just writes one single block in the journaling area, right? So that's why what we do is we do the block read to essentially read the header. We do this trick when we essentially typecast the data area of this block, which is in a buffer cache, to the log header, right? We just update the number in the log header, and then we essentially copy all the blocks, right? at this point, remember that the log header exists in two places. It exists on disk and it exists in memory, right? So we copy the data from memory to disk, right? And then we essentially write the block and release it, right? At this point, the transaction is actually committed on disk, right? At this point, if we lose power, again, we will recover and reinstall this transaction. And however, if we don't lose power, right, what we do here is we install transactions with this install transaction function. So install transaction essentially goes over the journaling area, reading the block one by one, right? And essentially at this point, you say, look, I'm reading a block from the journaling area. Then I will next read the block where the data should go on disk, right? Then you do memcpy, copying data from one block to another. Again, write the block to disk and release both blocks, right? At this point, you don't need them anymore. And this write actually promotes the data to the data area of the disk, right? And then finally, you, again, as I was saying, you finish the transaction by updating the log header number to 0, writing it to disk, and you're done. Okay, let me stop here, but I somehow feel that people didn't get this journaling idea because of the technical issues with how I was drawing. So let me quickly, at this point, like draw it again, right, for you, but in a better form, just because I have a much better way of drawing here, and I hope that my pen will not be delayed so much, right? So this is your disk, right? I just want you to understand how it works for sure. This is the journaling area. This is the data area, right? And note, some of the transactions might actually touch the inode area, right? And they also can touch the free block area, so the bitmap, right? Because when you add a block to a file, essentially grow the file by 1, you have to write into the bitmap area to make sure that you mark this individual block as taken, right? Agree with this? So how you do the transaction, you say, look, op, you say begin op, right? Then you do something like a b-read of a block. This block, imagine this is block number 55, right? You say, please read block number 55. You obtain a pointer here. This guy gets, by the b-read function, gets fetched into the buffer cache, right? So we will allocate one block into the buffer cache, right? And essentially this block will contain the disk block number 55, right? Agree with this? Then we update data of this block, saying that b data equals to something like maybe some memcpy, maybe you do some update here, maybe there's some update here, right? Then you do a primitive which is called a log write. This log write, which takes this block, essentially what it does, it uses yet another data structure, which is called the log header. It's also in memory. This is log header, right? This log header has entries, and you record in the entry that this block in the buffer cache is part of the transaction now, but you don't do any writes at this point, right? You agree? Then you do a bunch of those, like maybe you updated a couple of those blocks. Maybe you updated block number 17, which was here, right? And some other blocks, right? Let's imagine we updated 2. So you will have 2 entries in the log header, right? At this point, because you did another log write of the second block of block number 17, right? Agree? This one is block number 55. At this point, you say, okay, and op. And op does the following. Let me change the color here to blue. And op says, okay, look, I got it. I understand that I have to promote those blocks, those 2 blocks which are in this log header, to the journaling area. I will first take a look at this block number 55, because I have a reference to 55 here, and I will write it into the journal, into the journaling area. So essentially just doing this write. Agree with this? So this is now block 55, which got written here in a journal, right? Then you say block 17, which is written in the next block in a journal, right? So this is number 17. At this point, you say, look, I will write the whole log header into the transactional, into the header of the transaction here, right? So those entries will show up here, and I will write also additional size of this header, saying that there are 2 pending entries waiting here, right? At this point, your commit function is done, and you do install transactions. And let me like use another color. At this point, you say, look, I will be working this list one by one, right? And moving this into block number 55 here, right, on disk. And I will be moving this one. I lost my pointer. Oh, hold on. I will be moving up. I will be moving this one into the 17, right? Agree? And once I did those writes with bwrite functions, right? Because you really write the disk with the bwrite. Those blue ones were also bwrites, right? So those were block writes. Bwrite into the journaling area. So which block did you write? So if this is block number 0, this is block number 1, this is block number 2, this is block number 3. So this block write actually wrote block number 2. Agree with this? And the second one was wrote bwrite. This one was writing block number 3. Agree? It's just part of the journaling area. And then when we wrote the log header with this bwrite, we wrote the block number 1. Agree with this? And then when we install the transactions, we wrote those blocks from the journaling area into the data area. And then one last write will be performed when we completely finish the transaction. We write this block again. So we write this one, block number 1 again, to essentially change this to 0, saying that the journaling area is empty again. So, okay, at this point, I believe I explained it well, right? So, okay, tell me, are there any questions about it? All good? Or everyone is just saying, okay, let's just get done with it. There is at least one person who wanted to attend this virtualization lecture. That's the only crazy person. Everyone else is like, okay, forget it about, like, just let's do the final and be done with it. Okay, no, I hope it's not the case. I've seen a couple of people who, not true, yeah. I know, I mean, I talked today with a couple of students in the office hours, and I was impressed. So people were actually like digging the system call assignment really deeply. So I was pleasantly surprised how well people decided to understand the x86 kernel. So that was pleasant. So I hope everyone, that's why I extended the deadline, because I thought, okay, like people are really trying hard. So let's do it. Okay, we got the journaling thing, right? Let's move on to the next one, to the iNotes. Journaling, again, I'm pretty sure you will be able to read the source code and understand. As long as you can look at the picture which I had on the screen, inherently the logic is simple, right? You just have to like trace through the code. But I'm confused about why this one block is still dirty and how is it released from the buffer cache. I'm curious to understand myself. So I will go ahead and read the source code after the lecture to make sure that I understand it. Okay, let's move on to the inode layer, right? So inodes are those unnamed files on disk, right? So remember the layout of the file system again. So there was this area which was containing inodes, right? And it's an area which consists of multiple blocks, right? And then each element of this array is an inode. And this is exactly the element of this array. We already talked about it, right? So there are like 12 direct references which point to the blocks which contain the data of the file. And then there is one pointer to the indirect block which contains other 128 references to the blocks which contain the blocks which didn't fit in the first 12, right? Okay, so this is this area, right? Right between the journaling area and the bitmap, right? And inodes are literally stored as an array on disk, right? Each inode has a number which indicates the position in that array, right? And the kernel keeps a cache of this inodes in memory just because it's faster, because inodes are accessed multiple times, because as you write more data to a file, you will grow the size, and then you only once flash the inode back to disk, right? So, okay, let's take a look at the representation of the inode on disk. So this is this disk inode data structure. It has a type, file type. It has a major and minor device numbers, if it's not a file, but a device like a console, right? Number of links, so number of times the inode was added to different directories, right? And has a name. When this number drops to 0, it's time to essentially release the inode. Size of the file in this 12 direct blocks plus 1 indirect block, right? Okay, kind of makes sense. This is exactly the same picture. We already counted the size, right? So we did this multiplication. And this is the data structure which represents inode in memory, right? It has the same field, kind of like device number, inode number, reference count, flags. Those fields actually are not like, those are new, right? Because you say, look, number of references is actually number of references inode is actually currently used by the operating system kernel. So essentially, it's kind of like a reference counting here. Again, when the reference count drops to 0, it's time to flash inode back to disk, right? So, and the operating system maintains a cache of inodes, essentially just an array of these inode data structures in memory. And when you read an inode from disk, you essentially allocate one inode from this, one unallocated inode from this cache, right? So numbers don't match. So on disk, you might have 512 inodes, right? So it's kind of similar to a buffer cache. And maybe this inode cache has only like 32 entries, right? You just say, look, when I read inode number 55, right, I will get it here in this array, right? So it's kind of similar to a buffer cache, but for inodes, right? So there's a couple of functions which allow you to allocate and deallocate inodes on disk. And as I was saying, reference is a counter of how many times this inode data structure is currently referenced by the operating system kernel, right? So, and this reference counter is incremented and decremented with this iget and iput functions, right? So the way it works is the following. This is a typical sequence of how inodes are accessed. So first you say, look, similar to how you were doing bread, right? You do the iget function, providing the device number and the inode number. And it gives you essentially, it searches for an empty, it first searches, okay, maybe this inode is already in the buffer cache, right? We'll take a look at in a second at this implementation. If yes, you will like just return a pointer to it. If not, you will really read the inode from disk into the buffer and essentially synchronize the fields into with an entry in this inode cache, right? Then you acquire a log. If you want to do modifications to this inode, you acquire a log. You can examine and modify it, right? Change the size or something like that. Then you release the log, and then you put decrementing the reference counter, right? So let's take a look how this iget works, right? So I was saying, so you first acquire the icache log, sorry. Then you check for the fact that this inode is already cached. Again, it's a linear scan. And here we don't actually do least recently used. We believe that this array is small. It's not the most efficient way to do that, but essentially you go from the beginning of the array to the end of the array, and you're trying to find an inode which has a greater than 0 reference count, and the device and the inode number match the ones which you provided as input to this function, right? And if you found it, you increment the reference, right? It's atomic because you're already holding the log, right? So now you understand synchronization. So you because on the other CPU, some other processor might try to open the same inode, right? So because you resolve the file name, and maybe these are even 2 different file names, but which resolve to the same inode, right? However, if inode is empty, and hopefully that, as while going through this buffer cache, essentially what you're doing here is you say, look, you're trying to remember the empty position in the list, right? Because you go through the entire list, but as soon as you see one empty element, you remember it. Because if you don't find this inode that you're searching in the list, right, you will then take an empty inode and try to make sure that you will, like, you're located a new inode at this point, right? Okay, let's take a look. After you get the inode in memory, there are two main functions which allow you to read and write data of a file, right? We saw these functions when we were doing exact system call, right? So we saw the read inode function, which essentially I was saying, okay, we use a name I function to resolve the name in a file system to an inode. And after that, we were using the read I function to essentially read the inode itself, right? So for example, when we're doing the sysread system call, right? You say, I'll get a pointer to a file. Do you remember where this F comes from? Which would
Trap frame, context trap frame.
From where?
Trap frame, it's the system call, like
Not the trap frame. Come on. This function, which translates the argument to a file descriptor.
Isn't it like the context?
No, I mean, it's a good thinking. Look, this is the user stack. The user has passed an argument saying that I want to read file descriptor number 17. And then invoke a syscall. Inside the syscall, you created the trap frame. And of course, you have a context here as well, right? You have the context only when you context switch, but you're doing the syscall, so you don't really have a context yet, right? There are just some additional members which get pushed, like return addresses as you go through the kernel, right? And this function argfd essentially takes the ESP, user ESP, which is saved as part of the trap frame, right? Access it. Okay, this is ESP. This is how I can write today ESP over user stack. Then you essentially carefully get this number with all the check to make sure that this 17 is within the user memory. And then what do you do with this number 17?
Push into F.
Like pushing it where?
F and F.
No. Inside the process data structure, there is an array, which is called what? It's called
open files.
Open file descriptors, or we were calling it a file descriptor table, right? And this 17 is essentially a position 17 in this file descriptor table, and this will have a pointer to the file, right? Data structure. That's how it works. Agree?
The 17 is taken from the stack pointed by the context, and then the 17th is the pointer within the list of files, right?
Correct. So
okay,
hold on. It's not a context, it's a trap frame. Trap frame contains the pointer to the user stack, user ESP. In this case, there is no context because we're not context switching. Right, so we're still within the syscall. Only when we start switching, then we will have a context, right? Agree with this?
Yeah, got it.
Got it. I mean, I cannot recognize voices. I'm sorry. But I mean, it looks like you were working on this exact system call homework quite a bit, right?
Yeah.
Yeah. Okay. So, but okay, does this help? Does this clarify what's going on?
Yeah.
Okay, good. For everyone else, I hope it's also useful. So, okay, we got this file data structure, right? So I'm here, I have this explanation, how we access this file descriptor table. We already talked about it, right? Maybe it's actually, oh, it's not even an array here. It's just a pointer to an array. No, it's an array actually, right? It's an array of pointers, I'm sorry, right? And so this is the struct file, right? And it can either point to a pipe or it can point to an inode, right? And there are can be a couple of fields here, whether it's readable or whether it's writable, right? Agree? So when it points to the inode, right? So essentially, as I was saying, this is how the file read function is implemented. If you're doing a read and the readable flag is 0, then you return -1. If the file type is a pipe, you do a pipe read function, and it's a different function, right? We looked at it when we were doing synchronization, if you remember, right? We were, oh wow, I'm close to, actually, I was very close to losing power. It's good that I noticed it. I stepped on my power bank. Today is like such a bad day, like Zoom doesn't work, power is disconnected. Everyone wants to be done with this class. Okay, but however, if it's not a pipe, right? If it's an inode, we will be using this read inode function, and we will use these two primitives. We will first lock an inode. Where does the inode come from? It's already here. It's a reference from the file, right? Because when you open a file with the file open system call, right? At that point, you did this iGet. So right now you have the following. You have the file, and the file is pointing to an inode, right? Agree with this? And if you have a file descriptor table, there will be a pointer to this file. The same file can be opened by another process, right? So another process can have a pointer like this, right? And this is how two processes can both invoke an open system call and then get a pointer to the same file, which will lead them to the same inode, to the same file and disk. Got it? And now we're descending into this read inode function, right? Agree? Here we said, okay, reading of an inode requires atomicity, because if another file will be concurrently modifying inode, then your read might be inconsistent, right? So that's why you're acquiring this lock, ilock in line 5724, and then you release it at 5727, right? Agree with this? Let's take a look at this read I function. You start reading from this, from an offset here, and address is an address of a buffer where you read it, right? So this is the read inode function. So first of all, you do a check here. What are you checking here? Who can tell me? It's an offset within a file plus n.
Is it to check whether it's it's within this block or something like that?
It does two, like first you're checking if the offset is outside of the file size. Okay? That's an illegal read. And the second check is to check that the offset plus n is actually within the file as well, right? So n is the size of the read. Offset is an offset within a file. Destination is a destination buffer. Inode is an inode pointer, right? So it can overflow. And after that, you say, look, I will be reading the file block by block, starting from this offset, right? So let's take a look. There is yet another layer, which is called, it's not a layer, but essentially you say, look, this is the bmap function, right? Bmap function takes a number and essentially walks this tree, essentially, when you say, look, if I am reading the offset is within the first block, I will use the first entry within the direct block, right? One of these 12 direct entries. Then the second entry, third entry, and at some point you say, look, I'm reading so far into the file that I actually have to go through the indirect block right here, and then maybe read this pointer, right? Do you agree with that? It's kind of like it reads this mapping. It's kind of walking the page table, but for an inode. And this function is called bmap, right? So essentially you're looping here, reading it block by block, right? This is the explanation for this bmap function. So bmap essentially, you say there is some address. Let's imagine it's 612. You're reading address 612. 612, you first divide it by 512, right? To understand, you're doing this modular operation here, right? No, you're division and you're taking what? You're taking a
the integer representation and
yeah, you're dividing to essentially understanding, okay, so this will give you 1, right? This division. And this division will not land you on entry 0, right? Because if you would be dividing like 412 by 512, then you would get 0 here. But you get on the entry number 1, then you take this pointer and essentially read the block which contains this data, right? So it's essentially like walking the page table, as I was saying, right? If you, however, like fall into the range where you above the indirect blocks here, you will read one of those entries, right? You agree with this? Do you understand how it works, BMAP? Let's take a look. So essentially you say, look, if my block number is smaller than the indirect, smaller than 12, then you just simply say within the inode, since I already read it from disk, I will just in this array will locate the essentially the address, right? Of this. This is the disk on, this is the block number on disk. It can happen that, you know, this block is 0, right? BMAP is a generic function. In case of a read, it cannot happen because in case of a read, we're already checking that we're reading within the range, right? However, if we are reading, if we're using BMAP inside the write function, we will allocate a new block essentially on disk, update this address, and update the inode saying that, okay, look, now you have yet another block because you didn't have it. The file grew by 1 block larger, and we updated your inode data structure. At the end, you return the address, which is a block number on disk, right, from the data area. If, however, this check fails, you subtract 12 from this number, right? And you say, look, now, if it's the larger than the number of the indirect blocks, again, it's an error. But if it's smaller, right, you will do the following. You will take the address of the block, right? So essentially, this is your inode. Oh, sorry. Where's my drawing here? This is your inode. You read this very last entry, right? This is this. This is the address of it. So block maybe 77 on disk, right? Then you say, look, I get this 77. If it's 0, you might need to allocate it, right? Again, doesn't happen during the read. Then you read this block. You read the entire block, which is 77, into this block pointer. You convert this, the data array, the data area of the block, 512 bytes, to this A, and you use the A as an array. So essentially you use this as an array, and you say this is the block number element here, right? Again, you say, if it's 0, you will allocate a block. Again, cannot happen. At this point, you have to do a log write. Why do you have a log write here? Because you're writing this block, right? So you wrote A is a pointer into the data of this block 77. So you updated it. So that's why you're doing log write. And it has to be atomic, right? So it has to be consistent. That's why you don't do B write directly. Maybe this transaction will never finish. That's why you're saying I will be using a log write function, right? And then eventually when you're done with this whole thing, you release it, right? Because you no longer need it. Do you agree? Do you understand how it works? Essentially, you just descend it into this layer and read an entry from the array there. Then if you need, you allocate the additional blocks as you go, in case when BMAP is used inside the write function, for example.
We need to check whether it's a write call, right? Otherwise, for read also it will.
So for read, I agree. I would write it the way you just said, but for read, we already checked here. So if we say that the offset is larger than the file size, we just return -1. And if the offset plus n overflows, right, you are allowed to read. So for example, you can say like there is like 2 bytes. I'm trying to read 512 bytes, right? But there are only 2 bytes in the file before it ends. That's why you adjust here. So you make sure that you only read enough, only read the bytes which are within the file, right? This check essentially corrects for the fact that the offset overflows. So essentially, maybe you are so smart that you pass this offset, which is very close to FFF, right? In this case, offset plus n actually overflows, right? Which might pass this check, right? That's why you guard against it. Do you understand? It's an integer overflow attack, kind of.
Yeah, got it.
Yeah. It's a little bit contrived here, but again, by knowing the high level idea of what's going on in the file system, you essentially will be able to read the source code. Okay, so we read it, right? You said you wanted to guard, we guard it inside the read function. Although I would agree that maybe a flag would be a good idea, but since we're already guarding against it, maybe it's not necessary, right? Okay, so this is the explanation of the same, how we read everything, right? So that's essentially the end of my explanation of the inode layer, right? So you got the point. So inodes are cached in memory. We can read and write them, and a syswrite and sysread are implemented in terms of reading and writing inodes, right? And obviously all the updates to inodes are within a transaction. So we just assume that the operating system is good enough to start a transaction. That's why essentially this one will update the transaction, right? And the bmap function is responsible for essentially resolving logical addresses within the inode into the physical addresses on disk, right? Physical block numbers. You agree? Okay, so the next layer, which we have to touch on, is a block allocator. I don't spend much time here, but block allocator is simple. Essentially, it's just a giant bitmap. There's just a little bit of complexity at how you calculate the specific bit numbers. So I don't want to really even spend time. This is the block alloc function, which essentially searches the bitmap, reading it one by one, does a lot of those low-level math bit operations just to figure out which bit is like which bit we're currently accessing, right? So you will be able to figure it out if you want, right? The major disadvantage of this design is what? Is linear scan, because every time we want to allocate a block, we'll have to search for the entire array. And as the file system gets more and more full, right, your search will take longer and longer. And it used to be that we had a homework which we were doing those writes, and we were like printing time. So essentially, initially, the time was progressing reasonably fast, but then at the end, every time we do a write to a file, because it allocates a new block, we were slowing down with every write, essentially up to the point that it was unbearably slow, right? That's because every time you do a write, right? Every time you do a write, your function, which does the bmap, will try to allocate an additional element, right, for the file, right? And essentially, this will require a search in this bitmap array. So a better organization, some caching of this array would be beneficial, right? Obviously. Okay, a little bit of an explanation, but we get quickly to the next layer, which is called a directory layer. So directories, as I was explaining, just special inodes. A directory is a sequence of directory entries and inode numbers. So roughly speaking, if this is a directory inode, it will be, you can view it as a table. So kind of a file name like foo here, and then the pointer to the inode, meaning the inode number 55, right? Each name has a max of 14 characters, right? And it has a special inode type, T_directory, right? Dir lookup searches for directory within a given name, and dir link adds a new file to a directory, right? So let's take a look at how these functions are implemented. Again, x86 uses the following representation of a directory in memory. So 14 bytes for the file name and an inode number, right? So dir lookup essentially says, okay, you're giving me an inode, and I will first check that this inode type is a directory. If not, I will panic because something catastrophically bad happened and we somehow got confused about this inode. Then, obviously, if you're searching for a specific file, you have a name here, right? File name. You say, look, I will search through the entire directory, right? I will be reading this inode with a regular inode function, passing the directory inode inside, right? I will be just reading entry by entry, right? We just looked at the entry type just on a previous slide, right? Using the current offset, and we'll just be reading the size of one entry, not super fast, right? If we fail to read, okay, that means that, okay, the directory somehow is corrupted, right? If we, what is this check? Not sure. Here we compare that the name of the entry which we read and the name which we passed inside here match. If they match, we return the offset and essentially get the inode number from this entry, and we acquire the inode, right? Because what the function returns is the inode, right? It's the pointer, like essentially what I get is the function which essentially reads the inode from disk into the inode cache, like increments the reference count by 1 and essentially returns the pointer to this inode, right? So do you get how it works? Essentially just look through the through all entries in the directory. Again, I just said that I'm not exactly sure what this check is doing. It's inode number 0. Inode number 0 is probably special, but I don't remember why it's special. So let's double check later, right? So, and the next layer, which we should care about, is the pass names, right? So essentially, it's the layer like name-I, which essentially takes this string and essentially moves from one directory into another until it finds the inode which corresponds to this file, right? And there is a special function which is called this name-I, which takes a string. If pass starts with a slash, evaluation starts from the root. Otherwise, it starts from the current directory. And remember, the process, the proc data structure has a pointer to the current directory. And a current directory was an inode. Do you remember this? I mean, back then it wasn't clear why would we do this, right? But now we kind of got better with this x6, right? So now we understand, right? So if we go edit proc h, right? So this proc data structure will have this current working directory here, right? And this is the pointer to the inode of the current directory. That's how it's implemented. Okay, let's take a look at how this search is actually working. So name-I essentially calls a helper function, namex. Namex itself starts doing this check, like if the pass is the pointer to the string, right? So the string can be like foo, bar, and then baz, right? Right? So it says, okay, if pass, which is pointing right here, right now, starts with this character slash, we'll get the root device, right? And the file system knows that the root device and root inode have special meanings. So root, yeah. And so it can open them because it knows where these are. So essentially, when you create a file system, you make sure that those numbers match, right? And so you say, look, this is an inode pointer, right? And we got some. However, it doesn't start with a slash. You go to the proc current working directory inode and duplicate a pointer. So idup effectively increments a reference counter to the inode, right? Now you will do implementing this, you will use this helper function, which is called skip element. So essentially, if you have a pass name like a/bb/c and name, right, you will say that it will split it into bb and c and setting the name to a, right? So essentially here, you essentially remember our pass was foo bar bas. We will separate foo out of it and the name will become bar and baz, right? So essentially pass will become foo and the name will become bar and baz, right? So skip element, we can take a look at this function, but you understand that it's just string manipulation. So you can probably easily write this function yourself, right? And what happens here is that for each of these inodes, which you essentially said, okay, this is the pass, we'll use the directory lookup function. Hold on, for this name, right? So this is foo, and you say, look, I will descend. So I say, in this inode, be it a root starting at a slash, there will be a folder which has this name, right? It can fail here, right? And then you will return 0, meaning that you're trying to open a directory which doesn't exist, right? Otherwise, you say, look, this is my next element in this hierarchy, right? And then next time, I will be essentially, I will update my inode to be this next, and I will be iterating in a loop, descending one layer, one slash after another. Yeah, agree with this? Any questions about this namex? It's reasonably simple, right? So let's try to move forward. So, and this is how sysopen works, for example, right? So when you do a sysopen syscall, right, and you checked for those arguments, right? You start a transaction here, then you say, look, I will take a pass and I will resolve it into an inode. If we fail, transaction finishes here, right? If not, essentially we'll go into this allocating a file data structure, right? And this is this file descriptor layer. This is the last layer, which is at the very top, which is specifically provides support for the system calls, right? So each file is a data structure, as we just looked at it, right? So it also contains a reference count, right? Because it may be referenced from multiple processes and can be added to multiple file descriptor tables, right? It has those flags, readable, writable, can either be a pipe or an inode, right? So, and this is what we're doing here. We allocate a new file, right, from this file array, because again, remember that x86 doesn't really have a memory allocator. It allocates only pages, right? And it uses those pages for stacks and page tables. Everything else is kind of like statically pre-allocated in arrays, and those arrays, x86 just searches through them, right? So essentially linear search again for an element which is not occupied in this file array, right? Agree? At this point, we say, look, I have a file. Then the next function allocates a file descriptor. So what do you think this function is doing? Do you remember? What's the policy here? Remember when we were like closing file descriptors and duplicating them? The policy is to grab the first unallocated file descriptor with the smallest number. Agree? So this is this fd alloc in your file descriptor table. For each process, which process has a file descriptor table, right? We will be searching starting from 0 to the max, looking for the one which is unallocated. And if we found a file descriptor, we put the file pointer there and return the file descriptor, right, to the caller. Oh, we got to the end. Let me just give me a sec. So we allocated a file descriptor, right? This file descriptor we will return to the user. Do you remember this, right? So this is the syscall, sysopen returns a file descriptor here inside the EAX register, right? And essentially this is it. So we set the file type to an inode, and we set the inode pointer within the file to the inode, which we essentially open here. So essentially this concludes our story about the file systems. And it actually concludes our story about x86 as well, because this is the very last slide of this class. So and I congratulate you guys on like making it to the end, especially people who are live here, right? Are there any questions about x86 or anything? This is a good point to ask them.
One question I have regarding journaling is, can the write B be too large that it cannot fit in the journaling area?
It can. And that's why if you carefully start looking at this file write operations, I had the very same question, which when I was first reading the x86 source, edit file C. So if you do something like file write function, you will notice that it splits the write into multiple transactions like this. So look, it will be writing, essentially doing each write as a small transaction. Although the whole loop is much larger, this guarantees that it will fit. If you don't do this, then yes, the kernel doesn't have a protection, and you can say, look, write a megabyte, but your journaling area is only like, you know, a couple of kilobytes. So you might ask me, why is that consistent, right? Or if I can ask you on the final, actually, that's a great question. I should keep track of all these questions about Why is it consistent? Because one of these transactions might allocate additional entries in the inode, right? Which will affect the free bitmap of free available blocks, the inode on disk, right? And that's why they essentially they do it but transaction after transaction is consistent, right? Each small transaction is essentially consistent. Do you agree with this, or have any other questions?
I have another question.
Go ahead.
From the previous lecture. So in the when we have main.c, right? In that.
Can you speak up just a little bit? It's maybe I'm not sure my speakers work correctly.
So can you hear me now?
Yeah, I can hear.
So in main.c, you said k must come after start others. So why should it come after start others processes? So I was not able to get that answer.
In which function?
Main.c, when we are initializing the user, the first process.
Yeah, this is another great question. And what you want me to answer?
I'm not able to. I tried to find the answer. I have some ideas. Is it because the memory map till 4 MB, only one processor will get it? I have hints, but I'm not sure.
Is it because we only mapped up to 4 MB of data in the page table, and so we cannot allocate other stuff.
If we don't start others, only one process will get all the memories.
How about I will assign it as an extra credit, and whoever can answer will get it. And if no one wants, then I will answer after the deadline. And I'll give you a hint to solve it. So just try moving this function up. And
okay.
Move it before the start others and see why it crosses.
Okay.
Yeah, it's a great question, and I forgot. And it's not easy to. What's the question again? Let me repeat it here. So the question is, and by the way, if I forget and you want this extra credit, so just ping me on Piazza. I will make it officially as an extra credit if someone wants to attempt it. So the question is there is this comment which says this function must come after start others. Let's move it over here, because at this point you say, look, what can go wrong? We already allocated all the memory, so why is it it should run definitely, right? Make QEMU Nox start running. And suddenly it's not running. The question is why. Let's move it again. You don't even you have to attach a GDB and see what's going on, right? Let's open it again. Let's see. We move it after start others. Make human ops. Hope it should run at this point. It should. Well, it doesn't run. Maybe my tree is broken to begin with. Let's quickly do it. My tree is broken, I believe. Git diff. I could have broken git branch. Git check master, right?
Git stash would stash it.
Git pull. No, we're not gonna do a git diff. Make clean. Okay, let's check if it runs. This one works. Let's go again to main. Oh, sorry. again. No, this one ran. Really? Shouldn't run. I remember investigating this.
Is the QEMU running with one CPU or something, and that's why it's
Can be. Let's check, but most likely not. CPU. Yeah, one. You guessed. Good job. Well, you already deserve a credit. Like, you know how to debug this thing faster than I do, right? Good job. Good job. Yeah. Oh, okay. It doesn't boot. So yeah, I remember I was there. I had the very same conclusion. I wasn't able to answer, and then I understood. That's why I want you to, like, instead of just listening to the answer, just you're at this point where you can answer. So I trust you. You will be able. So just try to understand what's going on. Why is it looping like crazy with this x with 6? What's going on here? That's the beauty. You will learn how to debug those things. It's a big skill. Okay, any other questions? All good? Okay, then, as I said, I invite you to join today for the architecture class, which has a lecture on virtualization. But other than that, thank you. I mean, I appreciate your time for this entire semester, especially since, again, it's usually late. And good luck, guys. I hope you have wonderful careers in front of you. And everyone who did well in this class, the correlation is strong, you know. I know. I mean, again, I talked to a person who was like deeply vested in like debugging the exec system call, and that person has a position at Google apparently, right? So yeah, like it's not a coincidence. So, but I wish you all of you luck. I mean, I understand that not everyone will be doing operating systems, right? In the end. But people who want to do like serious systems programming, I hope that this class will help you to understand what's going on in the world. Okay, thank you. Yeah, see you hopefully live at some point. And again, good luck.
Thank you.
See you.
Thank you, Professor.
thank you.
Yeah, good luck, guys.